everyone. I hope that you can see us. So we have this week the last talk in this term in the IGAFIT Colloquium. And it's our immense pleasure to have with us today Virginia Vassilevska Williams from MIT. So let me tell you a few words about Virginia. She is right now an associate professor at MIT. She obtained her PhD from CMU in 2008, and then she spent several years as a postdoc in Princeton, UC Berkeley, Stanford, and then she became an assistant professor at Stanford University before she joined MIT in early 2017. She is the recipient of NSF Career Award, Google Faculty Research Award, Sloan Research Fellowship. In 2018, she gave an invited lecture at the International Congress of Mathematicians. So she's well known. She has done in the last 10, 20 years amazing research in graph algorithms, in various applications of parameterized complexity algorithms. And today, she'll be talking about three-sum, all-pair shortest path, and monochromatic problems. And before I will let her give the presentation, let me just remind you about the setup. So if you have any questions, please put them in the chat or Q&A, and I will just read it to Virginia. And other than that, let just Virginia take the floor. Thank you.
Thank you, Artur. Hopefully you can see my screen. It's my great pleasure to join you today. So I'll talk about three-sum and a few other problems like all-pair shortest paths. So let me describe the setup. Okay. So typically in algorithms research, what happens? So you study some computational problem A, and you have a bunch of techniques. So you throw all the techniques you can think of at the problem. And you get some running time, A of n, where n is the input size. And you optimize this A of n as much as you can. And then at some point you give up, I can't do anything better, and you continue doing a literature search. You do a very thorough literature search, and you see that nobody has been able to beat this A of n substantially. Maybe they got A of n over polylog of A of n, but not much better. And so there's a lot of these examples. You can look at satisfiability, k-clique, edit distance, diameter, longest common subsequence. I can go on and on. Many examples. And the question we want to resolve is, why are we stuck, and are we really stuck for the same reason? And this is where fine-grained complexity comes in. What do we want to say? We want to say if we have a problem A with some running time A of n, and a problem B with some running time B of n, and you want to define some sort of reduction between A and B, we call it an A-B fine-grained reduction, so that if you happen to be able to beat the B of n running time for B by a substantial amount, so you get something like B of n to the 0.99 running time, then you can also beat the A of n running time for A by some other potentially substantial amount. And if you have a reduction from A-B reduction from A to B and a B-A reduction from B to A, then you can show that they're equivalent for these running times. And why do we want to do this? So we want to say, if we can prove such equivalences, we can say, well, for these two problems, the reason why we're stuck on their running time is the same. And if we get a technique for one of them, then we can also get a technique for the same technique will work for the other one. And here's a formal definition of an A-B fine-grained reduction. Okay, we say that the problem A is little a, little b reducible to b, where a and b are running time functions. Maybe they're functions of the input n, or maybe n is some measure of the input size. For example, in graphs, it could be the number of nodes and not the actual size of the graph, but it's related to the size. Anyway, so we say that A is AB reducible to B if for every epsilon, there exists some delta and an A of n to the 1 minus delta time algorithm, so an improvement over A of n that solves A. But how does it solve A? It takes an instance of A and runs this algorithm that runs in A of n to the 1 minus delta time. But this algorithm is allowed to do oracle calls to the problem B. And the oracle calls could have different sizes. There could be many of them, and you adaptively call them. So in order to get the to build this one, you might need the answers for these ones. Anyway, so we have this algorithm that makes oracle calls to B, and the only condition that we need over here is that the sum over all the instances that you call B on over here of B of n sub I to the 1 minus epsilon is actually less than A of n to the 1 minus delta. Now, what does that mean? It means that if you happen to get a B of n to the 1 minus epsilon time for problem B, then you can replace the oracle calls with this algorithm on these instances over here, and then you will be able to solve A by composing the reduction with this algorithm for B over here, and the running time will be the running time of the reduction plus the sum of the running times of these little oracle calls. And the sum of the running times of the oracle calls is this over here, the sum over the running times for each n sub I. And this, our condition says that it has to be less than A of n to the 1 minus delta. So in the end, you get that A is an A of n to the 1 minus delta time. Notably, epsilon and delta can be different. Maybe you get like a 1/2 over here, maybe a 0.1 over here. But the point is that as long as you get some improvement over B of n, then you would get an improvement over A of n. And this sort of reduction, well, can allow us to get equivalences between problems of different running times, which is something that I find very fascinating. Okay, so that's the formal definition. Now, in fine-grained hardness, we pick several hardness hypotheses for problems that we really think are kind of hard. For example, CNF SAT, a problem 3-sum, and a problem all pair shortest paths. We formulate hypotheses about the running time of these problems, then use fine-grained reductions to explain the hardness for many other problems. Okay, so let me be thorough. We all know KSAT. You have n Boolean variables x1 to xn. We have a conjunction of m clauses where every clause is a big OR of a bunch of literals, k literals, and every literal is a variable or its negation. Okay. We want a Boolean assignment that satisfies all the clauses, or we say no, the formula is unsatisfiable. Right. So there's definitely an easy algorithm for this problem. We just enumerate all possible Boolean assignments to the variables. There's 2 to the n of them, right? There's n variables. And then you plug in every assignment and check if it works. There's actually, if you look in the literature, the best known algorithms look like this. There's this 2 to the n, and then in the exponent, you have 1 minus some constant over k, where k is the width of the clause, at times some polynomial in the number of variables. And the different improvements over the SAT running time, they basically improve these constants C and D. And as the width of the clauses grows, this running time goes to 2 to the n, which is the brute force running time. And so there's this strong exponential time hypothesis that basically says that you cannot do better than 2 to the n for k SAT as k grows. So for every epsilon, there's some width k for the clauses, so the k SAT on the n variables cannot be solved in 2 to the n to the 1 minus epsilon time. So you cannot get 1.999 to the n for all k. So this is a very widely believed hypothesis, and we use it in fine-grained complexity. It's used in fixed parameter tractability, exact algorithms, and so on. So here I'll define 3 more problems that I'll talk about in this talk. So these problems will be polynomial time problems, and I have to fix the machine model because depending on the machine model, you can have different polynomial overhead for the running times of problems. So I will fix the word RAM model with order log n bit words. So let's look at the 3. There will be 3 problems over here. Okay, so here's the first one, 3-sum. Here we're given a set of n integers, or numbers more generally, and you want to know if this set contains 3 numbers that sum to 0. There's a very easy n squared time algorithm for this problem. you can immediately see that, like with a hash table, we can do expected n squared time. Just for every A, B hash, their sum, and then for every C, check if the negative of C is in the hash table. But you can also do it deterministically and with like some finger search thing. So if you look in the literature, there's the best known algorithms for threesome running n squared over log n squared time times some polylog log, this is that tilde, is if the numbers are integers and you're in this word RAM model of computation. Chan extended this here also for real numbered inputs, but now in the real RAM model of computation, and got basically the same running time. So this is the best known thing for threesome, and the only improvement over n squared is the log n squared. And so there's this threesome hypothesis that says that threesome in this word RAM model of computation requires n squared minus little o of 1 time. So you can improve over n squared by some polylogs or so on, but you won't be able to get n to the 1.9. And this is a very well-established hypothesis. It came from computational geometry, and now we're using it for other problems as well. Here's another problem called orthogonal vectors. Here we're given a set of n vectors, and they're very short. They're in d dimensions, where d is just a little bit more than log n. Think of log n times log n, for example. And you want to know, are there two vectors in your set that are orthogonal? Now, these vectors are binary vectors. So orthogonality here means that for every coordinate in which u is 1, the v must be 0. So that's all that means. It's a very easy to solve problem. You can enumerate all pairs of vectors and compute their inner product. That runs in n squared times d time, but d is tiny, so it's essentially n squared, tilde all of n squared. The best known algorithm improves over n squared a little bit, but it's n to the 2 minus little o of 1 when d is much more than log n, which is this case over here. So this improvement here would only be a constant if d is order log n. But if it's more, it's less, it's little o of 1. So there's this OV hypothesis, orthogonal vectors hypothesis, that says this problem requires n to the 2 minus little o of 1 time in this model of computation. And Ryan Williams in 2005 showed that if you believe the strong exponential time hypothesis for SAT, you should also believe the orthogonal vectors hypothesis, because SAT can actually be reduced to orthogonal vectors in this fine-grained way, in the sense of a 2 to the n, comma, n squared reduction, in the sense that I told you before. So if you improve over n squared for orthogonal vectors, then you improve over 2 to the n for SAT. Third problem, all pairs shortest paths. We all know and love this problem. So we're given an n-node weighted graph. So we have arbitrary, let's say, integer weights on the edges, and you want to find the distance between every pair of vertices. There's a lot of classical algorithms like Floyd, Warshall, and so on that can solve this problem in n cubed time, where n is the number of nodes. And Ryan, again, with the same sort of polynomial method technique, showed that you can improve over n cubed by a factor of exponential of square root log n. But this exponential over square root log n is still n to the little of 1. So there's this hypothesis, the all pairs shortest path hypothesis coming from the graph algorithms community, that this problem requires n to the 3 minus little of 1 time. So we have threesome from computational geometry, orthogonal vectors basically from the satisfiability community and also from the database community, actually, if you think about it, and all pairs shortest paths from graph algorithms. And these three problems have been used to show hardness for a lot of things. So here's just a very partial picture of things you can show. So for threesome, there was a huge literature in computational geometry starting from the 90s by Guyentan and Overmars, who showed that if you assume that threesome requires n squared time, then a bunch of geometry problems also require n squared time. Like determining whether 3 points in the plane, you have a set of n points and you want to know if 3 of them lie on the same line. That requires n squared time, assuming the threesome requires n squared time. And also, more recently, we've been able to show that If you believe the threesome is hard, then a lot of problems in sequence alignment are also hard. So their algorithms are, the known algorithms are tight in this fine-grained sense. If you look at orthogonal vectors, there's an exploding literature of hardness from orthogonal vectors and therefore from satisfiability. For problems like diameter, edit distance, subtree isomorphism, Hamming closest pairs, and so on. Many different problems, even just in n-squared time, but you can go to other running times as well. Assuming that SAT is hard or orthogonal vectors is hard will give you tight hardness results for many problems. For all pair shortest paths, we have all these equivalences. So for example, all pair shortest paths, computing all the n-squared distances in a graph, is equivalent to some very simple problems, like for example, computing the radius of a graph, and so on. So they're like equivalent in terms of n cubed, where n is the number of nodes, or if it's a matrix problem, it's the number of the rows and columns of the matrix. Okay, so there's just basically this keeps exploding, and if you wanted to, sometimes people add other hardness assumptions to these main ones over here, but most of the results are from these, and they happen to be able to explain most of the places where we're stuck. Okay, so this is my introduction, and what I'm going to do next is I'm going to focus on these problems in the middle and talk a little bit about them. Are there any questions at this point?
No questions.
Great. Okay, everything is clear. Wonderful. All right, so let's talk about the three problems: orthogonal vectors, all pair shortest paths, and threesome. So there's a paper by Carmosino et al. Who show in 2016 that shows that if you strengthen the strong exponential time hypothesis a bit, then you can show that these problems are not all equivalent. And in particular, this strengthening, which may or may not be believable, implies that you will not be able to reduce orthogonal vectors deterministically to threesome or all pair shortest paths. So assuming this hypothesis, orthogonal vectors is probably harder than the other two. However, it says nothing about threesome or all pair shortest paths, and in fact, those two problems seem much more related. And there's no known barrier to proving that they're equivalent, so they might actually be equivalent. So let me show you some things that we know. Here's a big picture, so let me take you through it. So every one of these problems, orthogonal vectors, threesome, and all pair shortest paths, has some class of problems that are equivalent to it. Orthogonal vectors has problems that are n-squared equivalent to it. Problems like maximizing an inner product. So you're given n vectors, let's say integer vectors, you want to find a pair that has maximum inner product. And there's a bunch of these inner product-like problems that are equivalent to OV as long as the vectors have small dimension. And this equivalence class was discovered by Chen and Williams in 2019. All pair shortest paths has a huge equivalence class of problems, mostly graph problems like radius that I mentioned before, and they're all n-cubed equivalences. And we wrote this paper, Ryan and I wrote this paper in 2010, and then I wrote a paper with Amir Aboud and Fabrizio Grandoni in 2012, adding more problems to the list. And over here for threesome, there's a smaller number of problems that are equivalent to it, but still, there's an equivalence class. What's interesting about this equivalence class is that it includes problems with different running times. So Petrashko in 2010 showed that threesome is equivalent to a simpler looking problem called threesome convolution. And more recently, we were able to show that something called monoconvolution, a problem in n to the 1.5 time, is equivalent to threesome as well. So you have this weird equivalence class here. Now, I was mentioning that all pair shortest paths and threesome are more related than orthogonal vectors. And in fact, there's two very natural problems that these two problems are sandwiched between. So there's this problem called min plus convolution that it reduces to both of these problems, both to threesome and all pair shortest paths. So that if you improve over n cubed for all pair shortest paths, you improve over n squared for this one. And if you improve over n squared for threesome, you improve over n squared from n plus convolution. And also, there is a problem that both of these, both threesome and all pair shortest paths, reduce to. This is this exact triangle problem. You're given an n-node graph with integer edge weights, and you want to know if there's a triangle in the graph whose edge weights sum to 0. It's easy to solve in n cubed time, and improving over n cubed substantially would resolve both the all pair shortest paths and the threesome hypothesis. So this picture kind of shows you that these problems are much more related. Orthogonal vectors, we don't know how to, we don't have a problem that reduces to all three of them, for example. So what I'm going to do next is I'm going to actually show you some part of these equivalences over here. I'm going to focus on this monoconvolution problem and threesome, and I will show you how you can get a reduction, an equivalence between two problems of different running times. And then at the end, I'll conclude with some more thoughts on these three problems and how they relate to each other. All right, so I'll just focus on this equivalence. We have threesome. It's a given a set of n numbers. You want to know if three of them sum to 0. And monoconvolution is this other weird problem. So you're given three n-length arrays, A, B, and C. And you can think of the entries of the arrays as colors. Like you have green, blue, and so on. And it's a convolution problem, so that you want to know for every k, is there some I so that A sub I equals B sub k minus I equals C sub k. So the convolution part comes in the indices. It's I, k minus I, and k. And the mono means monochromatic, so the colors in position I, k minus I, and k are the same. So this is just an equality problem, and this is a sum problem, and somehow they're equivalent. So again, yeah, they have different complexity, and also there used to be this intuition that threesome is hard because you're kind of summing these largish numbers, and it's hard to reduce the range too much. So maybe that's why threesome is hard. But here, monoconvolution, the only summing that happens is in the indices over here. And there's no summing otherwise. And so the intuition that the large numbers cause the hardness might be flawed. All right, so more on these equivalences. So actually, there's a different problem that's also equivalent to threesome and monoconvolution. It's called all numbers threesome. It sounds like a generalization of the threesome problem. It's like this. So you have a set A of size n, and I want to know for every number in A, are there B and C in A such that A plus B plus C equals 0? Threesome just asks, are there three numbers that sum to 0? And here I want to know for every number in A, is it in a threesome? So it seems like a generalization. So clearly you can reduce threesome to all numbers threesome. But it turns out that you can also reduce in the other direction, so that if you can solve threesome in subquadratic time, you can also solve all numbers threesome in subquadratic time. We showed, Ryan Williams and I showed this in 2010. So these two are equivalent, and what I will show you is an equivalence between monoconvolution and all numbers threesome. So all these problems actually have a variety of variants that are equivalent to them. So for example, threesome has this colorful variant that is equivalent to it. So in the original version that I told you, A is a single set, and I want to know if three numbers sum to 0. But it's also an equivalent variant is it when you're given three sets, S, T, and U, and you want to know if there's a number from each set that sums to 0. And even more, you can, negate the numbers in one of the sets. So you can be asking if there's a number A, B, and C from each of the sets, so that A plus B equals C. So that's also threesome. It's an equivalent version. And the same sort of thing can be done for all numbers threesome. You can say, you're given three sets, and you want to know for every A in the first set, are there B and C in the other two sets, so that A equals B plus C. This is the same sort of problem, and they're all equivalent. So from now on, all numbers threesome, I'll take it to be this problem. And for threesome, sometimes it will be this one, sometimes it will be this one, and I'll tell you which is which. Okay, so let me focus on this reduction over here. you may ask, why am I reducing between monoconvolution and all numbers threesome and not directly with threesome? Well, here's the usefulness for all numbers threesome. So often in these in algorithms and in reductions for threesome, you want to reduce the range of the numbers. And because it's a linearity problem, a plus b equals c or a equals b plus c, one usually takes, let's say, a random prime and mods everything by this prime and tries to reduce the range of the numbers. Now they're the size of the prime instead. And if you assume that the integers in your threesome instance or all number threesome instance are bounded by polynomial in n, you can pick a prime from some range, like an n cubed sort of range for threesome, and make sure that if you union bound over all the triples of numbers, you will not make a mistake, roughly speaking. So for threesome, you can take, the range has to be basically n cubed, because there's 3 n cubed triples of numbers you have to care about. Now, for all numbers threesome, however, if you use such a hashing trick, like modding by a random prime, for example, then actually the range can be n squared, because instead of union bounding over triples, you're now union bounding over pairs, right? Because you have to output for every a, if there is a b plus c that equals to it, you only really care about the pairs b and c. So we know that threesome and all numbers threesome are equivalent, but for all numbers threesome, the range can be made smaller. And this is actually useful for reductions. Okay. So I've given you one tool. One is like reducing the range, and all numbers threesome is better. So I'm going to give you one more tool. Here's another tool that is used in threesome problems. If you take a threesome instance on n numbers, you can very quickly reduce it to g squared for any g squared instances of threesome on a smaller number of numbers, on n over g numbers. So g squared instances of threesome of n over g numbers. You can do this. I will show you very quickly one way to do this. Here's one way. You take your n numbers, you sort them. There they are, they're sorted. Then you split the sorted list into g intervals of n over g numbers each. You're basically in the sorted order, kind of bucket them into pieces. Let S1 be the start of the first interval, meaning that's A1. T1 be A sub g, right? That's the end of the first interval. And in general, S sub I is the start of the ith interval, and T sub I is the end, right? It's easier to write this way. So now what we're going to do is we're going to create an instance of threesome for every triple of intervals. And if we do that, we're going to guarantee that, of course, we'll catch every threesome solution. If we do that, we will get g cubed instances. But actually, we only need to create an instance only for that triple of intervals, so that 0 is actually between si plus sj plus sk and ti plus tj plus tk, between the sum of the start of the numbers in the intervals and the end, right? So that those are the only triples that could potentially have a threesome solution. And interestingly enough, the number of such intervals is order g squared and not g cubed. This is why you get g squared instances. So the way you prove this, I first saw it in a paper by Chumai and Linkas, by Arthur and Linkas in 2007 in a different context, so in a context about triangles. And we adapted the argument for threesome in this paper with Andrea Lincoln and Ryan, and yeah. So anyway, so this is a very useful technique. You can take threesome and split it up into pieces. So now I can give you an overview of how you can take this all numbers threesome problem and reduce it to monochromatic convolution. Remember, monoconvolution was this problem where you're given three n-length arrays A, B, and C, and for every k you need to output is there some I, so that C sub k equals A sub I equals B sub k minus I. So you're outputting an n-length Boolean array. So we'll take all numbers threesome. We're going to do this partitioning trick from the previous slide, where you take the parameter g to be n to the 1/3, and then you'll get g squared, meaning n to the 2/3 instances of all numbers threesome on n over g numbers, meaning n to the 2/3 numbers. And this is very quick, as I mentioned. So you create all these instances, you just partition the thing. Then you're going to do this modding by a random prime. As I mentioned, all numbers threesome, you only need to get a range that is quadratic in the number of numbers. So now you get a randomized reduction to n to the 2/3 instances of all numbers threesome on n to the 2/3 numbers, but now the range is small. Is n to the 4/3. It's quadratic in this. All right, so again, we've partitioned the all numbers threesome instances in a bunch of little instances that have smaller range. And then somehow we're going to take these many instances over here over a small range and produce a very tiny number of instances of monoconvolution on arrays of size n to the 4/3, which is the range of the all numbers threesome. Now, if we did that, then this will be, if the size of the monoconvolution array is big N, that's n to the 4/3, and if you solve this monoconvolution problem in big N to the 3/2 time, or less than that, then you would beat n squared for this problem. And so you will beat n squared for this problem, and then you'll beat n squared for all numbers threesome, and therefore for threesome. So this is how this reduction works, but how exactly do we do this? And that I'll do in the next 2-3 slides. Questions at this point?
So no questions. No question.
Great, thank you. All right, so this is the map of how we're going to reduce all numbers threesome to monochromatic convolution. So how do we do this step? So here's a very rough idea, then I'll get into some more details in a little bit. So the main idea is to take these instances over here and take their range. The range is roughly n to the 4/3 integers, so from 1 to n to the 4/3, and create an array of monoconvolution of that length. What do we put in the array? Well, we're going to use the colors in the monoconvolution instance to encode which of these n to the 2/3 instances the number came from. So in other words, if I find, so let's say I create instances of monoconvolution that are A, B, and C, then if I find A sub I equals B sub k minus I equals C sub k equals R, that will mean that the numbers I, k minus I, and k from the range appear as a threesome in the rth all numbers threesome solution. This is one of these over here. So that's what we want. The problem is, of course, that some of the numbers in the range could appear in multiple instances over here, and that's what we have to deal with. All right. So I will, in the next few slides, I'm going to try to explain how we deal with this. Okay. Again, this is what we're going to focus on. We take n to the 2/3 times log n. Let's say instances of all numbers threesome on n to the 2/3 instances over the small range. We want to produce a very tiny number of instances of monoconvolution over this array. And again, if we do that, then if monoconvolution can be solved in n to the 1.5 minus epsilon time, where big N is this, then you plug in big N and you get that all numbers threesome can be solved in n to the 2 minus 4 epsilon minus over 3. Okay. So here's how we're going to do this. Take these instances of all numbers threesome. Let's call that their number Q. Q is roughly n to the 2/3. Let T, this T, is some constant times n to the 4/3 is the range of, it's the range over here of the all numbers threesome solution. So the Q instances over a range T. Let's call all these instances here be A superscript I, B superscript I, C superscript I. So there's Q instances, and each one is one of these, AI, BI, CI. Suppose for a moment that there are no collisions. So in other words, the numbers that appear in instance I of all numbers 3 sum in the first array are different from all the numbers that appear in another instance. So all the A sub AI and B and AJs are disjoint, and all the BI and BJ are disjoint, and all the CI and CJ are disjoint. Suppose there's no collision, so every number from the range appears in at most one of the instances. This could happen, for example, if this log n weren't here and this big O are big enough, then you have n to the 4/3 numbers in the range. Each instance has n to the 2/3 integers, and there's n to the 2/3 instances, so you could have the numbers of the range are partitioned among the instances. But in general, it won't happen. But it's close maybe. So then, if there are no collisions, here's how we reduce to monoconvolution. We create 3 arrays, A prime, B prime, C prime, for monoconvolution. For A prime, we look at every integer A in the range, and we'll place it in the 8th position of this array. We'll place Q so that A is in the Qth instance of all numbers 3 sum. In other words, in the 8th position of A prime, we have that Q so that A is in AQ. Remember, there's no collision, so there's at most one instance of all numbers 3 sum that contains that number. We can also create like a dummy thing, let's say Q plus 1, larger than the number of instances that we put whenever the number from the range doesn't appear in any of the instances. Which is basically the same for B prime. We take a number in BQ, so the Qth instance, the B part of the Qth instance, we place Q in the 8th position of B prime whenever A is in BQ. Right, and some dummy Q plus 2 if that integer doesn't appear in any of the instances. And finally, we do the same for C. So in the 8th position of C prime, we put the index of the instance for which that A appears in the Cth list. Great. So these are the 3 arrays if there's no collision. And then if we solve monoconvolution on A prime, B prime, and C prime, that will compute for every C in the range. So meaning for every position in C prime. Okay. If there exists some a position in A prime, so the A prime A equals B prime C minus A equals C prime C. That's just a definition of monoconvolution, but now we have to translate it in terms of all numbers 3 sum. So it will compute for every instance over here, CQ, and every element of CQ, it will say, is there an A in the same instance and C sub A in the same instance, so that they sum to 0. So in other words, we solve the Qth instance for all Q, right? By putting the index of the instance that each number appears in here, we can solve all the instances of all numbers 3 sum, provided there are no collisions, just by checking for equality. So we'll have A plus B equals C whenever they appear in the same instance. Okay, so that's all fine and good, I hope. So we just encode in the colors the instance that the numbers appear in, except that the numbers in the range could appear in many instances, so we have to deal with that. How do we deal with this? We're actually going to do some random shifts. So for every one of the instances of all numbers 3 sum, there's n to the 2/3 log n of them, we're going to pick a random shift from the range into the 4/3 independently. And instead of solving AI, BI, CI, we're going to solve AI plus SI, BI plus SI, and CI plus 2SI, meaning that for every number in this array here, in this set here, we add the shift to it. And the same for every number in this one, we add the same shift to it. And for every number in here, we add 2 times the shift. Of course, because it's all a linearity, if A plus B equals C, then adding the shifts will also give us equality. So a plus b equals c if and only if a plus si plus b plus si equals c plus 2si. So the shift works fine. The solutions don't change by adding these random shifts, but what we do get is that we reduce the number of collisions by doing this. So for every value in the range, the probability that one of the n to the 2/3 elements of that instance of ai plus si is actually v. So for every v in the range, the probability that we get that one of the n to the 2/3 things actually maps to v after the random shift is at most n to the 2/3 over the range. Okay? And so over all of the instances, which there's only n to the 2/3 log n of them, the expected number of instances ai plus si that contain any particular v from the range is actually small. It's n to the 4/3 log n over t. It's only a logarithmic number of instances that any number from this range appears in. So that's great. So with high probability, we can also achieve it with high probability because the shifts are independent. So we can apply a Chernoff bound, and we can say for every number in the range over here, the number of all numbers threesome instances that after the shift that actually contain that number is only logarithmic. So this is great. We wanted constant. We actually wanted 1. We wanted v to appear in only one instance, but a logarithmic number is very small. So now we can fix our thing. We can say, well, we have at most a logarithmic number of instances that contain any particular v. So we'll just create an instance of monoconvolution for every triple of ijk in this set log n. For every triple, there's log n cubed triples, we'll create vectors. And how do we do that? Well, in the 8th instance of a prime sub I, we're going to put q so that q is the ith instance where the number a appears in. And there's only log n of them, so I only need log n of these sets, these vectors. And then we create a jth b prime, and we'll put in the index a q, so the q is the jth instance where the number a appears in, the jth instance of all numbers threesome. And same with ck. So here in the 8th position, we put q, so the q is the kth instance, so that a is in cq plus 2sq. We enumerate over all these ijk's. There's only log n cubed of them. And we get that after we solve log n cubed instances of monoconvolution, we get was solved whether for every c there exists an a, such that a prime sub a equals b prime j, c minus a is equals c prime k of c, which basically means that we solve all of the instances of a threesome, all numbers threesome for all q, by only running log n cubed instances of the monoconvolution. Right. So again, we're encoding which instance a number comes in, and we enumerate overall triples, and there's only log n cubed triples we need to consider after the random shifts. All right, so this basically explained this last step. So what we get is that we can take threesome on n numbers, go to a small number of instances of all numbers threesome on a small number of integers over a small range, and be able to reduce it in a randomized way to monoconvolution on an instance of size n to the 4/3. So this is how we get that if monoconvolution can be solved faster than n to the 1.5 time, then threesome can also be solved faster than n squared time. All right, so in the next very small number of minutes, I'm going to explain to you how to go the other way, how to reduce from monoconvolution to all numbers threesome. And this will be a reduction from a problem with n to the 1.5 runtime to a higher complexity problem of running time n squared. So in order to do that, I'm going to give you on one slide how to solve monoconvolution in n to the 1.5 time, and then I will very quickly replace one of the steps with all numbers threesome. And this will allow us to use a faster algorithm for all numbers threesome to speed up then to the 1.5 running time for monoconvolution. Okay, so let's do that one. So here's how we're going to solve monoconvolution. Remember, you have three arrays. They have colors. You want to know if there's three positions, I, k, and I minus k, where the colors match. So what we're going to do is we're going to look at the colors in the arrays. And there will be some colors that are heavy. And that means that they appear in at least square root of n entries of the arrays. They're heavy colors. And for every color, we're going to create three binary arrays that basically say where this color appears. So it's the indicator vector for the arrays. So for example, if array A looks like this and color 2 is heavy, then A of 2 is just, you put 1 wherever 2 appeared and zeros otherwise. And now that you have these binary arrays for every heavy color, you can use, so anyway, so you take these binary arrays, you do the FFT, and you can solve all the heavy colors in n log n time, and there's square root of n of them, so you can solve all the heavy colors in n to the 1.5 times polylog. And what remains are all the colors that appear in less than square root of n entries of A, B, and C, and those you can do in a brute force way. So for every light color of C and every color of A, the same color of A in the ith position, you check whether B sub k minus I also has the same color. And provided you've sorted the arrays and gotten the buckets of colors, this only takes n to the 1.5 time, right? Because every color, there's only square root of n other entries of the same color because the color is light. So this is brute force. So what I'm going to do is I'm going to keep the heavy colors exactly the same, and I'm going to replace the brute force step with threesome. Okay, so here's the very, it's just one slide. So what you do is you take a parameter t, and you say the color is heavy if it appears at least t times in the arrays in A, B, and C of monoconvolution. And as I said before, every heavy color can be solved in n log n time with FFT. So you can deal with all the heavy colors in n squared over t times some log. And now you have to deal with the light colors, those that appears at most t times in the arrays A, B, and C. And how do we deal with them? We create an all numbers threesome solution. We say for every light color V, you create three arrays, three sets. A of V contains those indices where A sub I equals V. B of V contains the indices where B sub j equals V. And C of V contains the K where C sub k equals V. All right, so for every light color, we have a tiny instance. And so if we solve all numbers threesome on these tiny instances for every V, we will know if there's an I, J, and K, where K equals I plus J, and the colors are exactly the same. So A sub I equals B sub K minus I equals C sub K equals V. So the all numbers threesome solution over here exactly solves monoconvolution for that light color. So it's just replacing brute force with threesome, basically. So now I have to quickly analyze the running time here. So n sub v is the size, the total size of this all numbers threesome instance. So the number of indices where you solve v in the arrays. And the sum over v of n sub v is order n. In fact, it's at most 3n. So the number of indices where v ever appears is at most the sum of the sizes of a, b, and c. So we have this nice inequality. So then if we can solve all numbers threesome in subquadratic time, n to the 2 minus epsilon time for size n, then you can write the running time for all these small instances to be the sum over v of n sub v to the 2 minus epsilon. Now every v over here was a light color, so n sub v is at most t. So I can take t to the 1 minus epsilon in front, sum over v n of v, which you said is order n, so we get n times t to the 1 minus epsilon. So instead of getting n sub n times t, with the brute force algorithm, we get n times t to the 1 minus epsilon. It allows us to balance the running times of the heavy colors and light colors. We get something for t, and the running time becomes better than a 1.5 for any epsilon that's bigger than 0. And this is how you get a reduction from a lower complexity problem to a higher complexity problem. You create many, many tiny instances and you solve them separately. So that's it basically. This concludes the equivalence. One word over here. So we said the threesome and all pair shortest paths are sandwiched between these two problems. They all have equivalences. There are some other problems that both threesome and all pair shortest paths reduce to. One of them is this very simple sparse triangles problem. You're given an m-edge graph, and for every edge you want to know if it lies in a triangle. There's no weights here. It's a sparse, unweighted graph problem. And it can be solved in m to the 4/3 time if omega of the matrix multiplication exponent is 2. And Yinzhan Xu and I showed that this exact triangle problem reduces in a fine-grained way to sparse triangles. And also it reduces to a monochromatic version of triangles as well, kind of like similar to monochromatic convolution, except now in the triangle world, you have an end-node graph with colors on the edges. You want to know for every edge if it lies in a triangle with exactly the same colors. The best running time here is n to the 2.5 if omega is equal to. If you can improve over any of these running times, then you can basically disprove the hypothesis for both these problems. OV still lies over here separate and alone, but there's actually some problems that you can reduce both exact triangle and orthogonal vectors to. For example, this triangle collection problem that we studied in 2015, and it turns out that, so it's very simple. N-node graph, colors on the nodes, is there's a triple of colors that has no triangle, or is it true that for every color triple, there's a triangle whose nodes have that color triple? And trivially solvable in n³ time, but if you improve upon it, you disprove all three. So this would be great. We still don't have a problem that is natural and reduces to all three, but there's something like this. And that's it. There's some open questions you can read.
Thank you very much, Virginia. So,
thanks.
Great talk. I really appreciate that. Are there any questions? So we are running out of time, but if there is still a question, feel free to shout in the chat. Let me check. So is randomization of any relevance here?
Is what?
Randomization.
Randomization. Yeah, I mean, we haven't tried too hard to de-randomize the reduction from all number threesome to monoconvolution. It would be very interesting. There's multiple steps, however, where we use randomization, but maybe there's a way to go around them. Right? We do the hashing, so you have to figure out how to, in a deterministic way, reduce the size of the numbers. And you also do these random shifts, so you have to find a way to do that. Maybe that's more doable. I don't know.
So you expect that this is possible?
It's probably possible, but it probably needs a lot of work.
I see. Okay. Any more questions to Virginia? I don't see anything. So let me thank Virginia again. And so this is our last talk in the series in this term. So I hope to see all of you in the next term. I hope that we'll run the series. There are lots of congratulations. And right now we'll move to the tables. If any of you will have any questions to Virginia, there is still time to do it. So we'll finish this session now, and Virginia also, please take a table in a second.
Okay, thanks.